So I don't know if a lot of you watch TikTok, and probably 20 years from now, when someone looks at this video, they'll laugh just because I said TikTok. But anyway, I have this one surgeon on there, and every time that I flip through his TikTok, he always says, "This is my favorite procedure," no matter what procedure it is. And I know sometimes I do the same thing when I say that this is really important. You really need to know this because I say it about so many different things. There's one thing about this section. This is one of my very favorite sections. And I think because I didn't learn this really in high school, and I thought, boy, if I would have known that then, it really would have helped me understand some things. So let's see. Maybe it'll be your favorite. In this section, we're going to look at some vertical shifting, horizontal, reflecting graphs, vertical stretching, horizontal stretching and shrinking, and even and odd functions. Already sounds exciting, doesn't it? We're going to study how certain transformations of a function affect a graph. This will give us a better understanding of how to graph functions and what they look like. And the transformations that we study are shifting and reflecting and stretching. First, let's look at vertical shifting. So anytime you add or subtract something to a function, you're going to cause it to rise or you cause it to fall. So for instance, if I have this function here, and it's not telling you what the function is, it's just saying any function in general. If I would, again, add a value to it, I'm actually just lifting it up that value. If I subtract the value from it, I'm actually just dropping every value. So I'm just taking this function and I'm either lifting it up or dropping it down. So let's take a look at the graph y equals x squared. And I'm so used to saying y equals. I know it says f of x, but again, it's the same thing. And I told you before, you need to know these parent functions. And the parent function, y equals x squared, looks like this. Okay, so hopefully you remember that and you heeded what I said and you know that this looks like this. Now, what happens when I add 3 to it, and what happens when I subtract 2 from it? Well, if you see here, this is my parent function that I told you before that you needed to know. And if I add 3 to it, I just simply lift it up 3. And if I subtract 2 from it, I just drop it down 2. That's it. So I'm going to observe that what I'm doing is I'm just taking that function, that parent function that I knew before, which we call x squared, and I'm just raising it up 3. Similarly, the other one, when it says minus 2, I'm dropping it down 2. And that's it. And you can do it with any function that you have. So if you add something to it, you just raise it up. If you subtract something to it, you drop it down. So now let's take a look at how it shifts from left to right. If on the inside I take my domain and I add a value to the domain before I plug it into the function, or I subtract a value from the domain before I plug it into the function, then that causes it to shift left and right. Since x minus c is c units to the left of x, it follows that the graph, when you put this in, will be shifted to the right. So be careful because a lot of people get these mixed up. And you want to make sure that you understand if you're subtracting a value to your domain first, you're causing it to shift to the right. And if you're adding something to your domain, then you're causing it to shift to the left. So again, adding to the domain is to the left. Subtracting from the domain is shifting to the right. So here we go. Here's just the general table that just defines it for you. If I subtract C, I'm going to move it to the right C units. If I add C, then I'm going to move it to the left. And again, the difference between this one and the last one is I'm adding it to the domain before I put it into the function, not adding it to the entire function afterwards. So here's my function. I subtract a value from the domain, I shift it to the right. Here's my function. I add a value to my domain, I shift it to the left. Here's some examples. So the first one, we're seeing that we shifted to the left 4 units. And the second one, we shifted to the right 2 units. Here is my parent function that everybody is supposed to know. Again, right here, if I add 4, I'm going to shift it this way, shifting it to the left. And if I subtract 2, I'm going to shift it to the right 2. That's it for that. Now, let's look at how we reflect graphs. So I want you to think about what you think is going to happen when we reflect something. We're going to take a look at whether I make the entire function the opposite of what it was, or if I am taking the opposite domain value and then inputting it into the function. If I'm taking the opposite of the entire function, then it's simply going to be the negative of the coordinate that it was. So it's going to really be, and they say the negative of the coordinate of it was, but the opposite. So if it was positive, it's now negative. If it was negative, the negative of a negative is a positive. So the desired graph is a reflection of the graph about the x-axis. What do you mean about the x-axis? Well, let me take this here. Here I have the x-axis. I'm going to reflect it about the x-axis. So if it's here, I might reflect it over here. So I'm going around the x-axis. On the other hand, if I take the value of the domain and I'm taking the opposite of it first, then I'm going to reflect it about the y-axis. So the y-axis is up here. So I'm going to go about the y. Well, I might be down here, but the y-axis is the vertical axis. So I'm going to reflect about the y. So here's an example of, I might have my original graph up here. This is my f of x. But if I make it negative, the whole thing negative, I'm just going to flip it around the y-axis, or the x-axis, I'm so sorry, the x-axis, and then it's going to now look like this, a mirror image. The same if I do the inside of the domain and I make that value negative, I'm going to flip it about the y-axis. So instead of this way, now I'm going to have the mirror image over here of this way. So that's my reflection. So let's take a look. Now, hopefully you recognize the x squared again as our parabola. Think about what you think would happen if I made the entire thing negative. What will happen? And then here's also my parent function of my square root. What will happen if I take the inside, the domain, before I plug it in and I make it the opposite? Let's see if you're right. Okay, so we start with this one. Again, here is our parent function that by this time you're tired of me saying that you should know it. So there's your parent function of y equals x squared. And if I make the entire thing negative, it just flips about the x-axis and it becomes the red parabola here. You might remember back a couple videos ago, I mentioned about the highest degree being negative, and that's why it was downward, and this is why, because it causes a reflection. If I take the domain on the inside, the x value, and I make it opposite, then what happens is I am flipping it about the y-axis, and what happens here is I now have this graph. And let's remind ourselves how to read this. It is for all x such that x is less than or equal to 0 when I have the reflection. Okay, so there's your reflection. So now you've learned how to move them up, move them down, and then reflect them about the x and the y axes. And that works for no matter what function you're using, which I think is super cool. So now we're going to look at vertical stretching and vertical shrinking. So what do I mean by that? You're actually taking the function that in its graph and you're stretching it, or you're shrinking it. Let's take a look. So here we have this function, y equals f of x, some function. And then what happens to it if I then multiply it by a value? The y-coordinate, y equals c times f of x, at x is the same corresponding y-coordinate, but it's multiplied by c. So it either goes up or it shrinks. Now it depends on if c is a number that's bigger than 1, or if c is a fraction that's between 0 and 1, whether it will be stretched or shrink. So again, very important here is I'm saying this is bigger than 1. This was my beginning graph. And if I multiply it by a value that's bigger than 1, then I'm just going to stretch it from here up to here, just like I'm pulling it here to here. But if it is a fraction that's between 0 and 1, let's say, for instance, I am taking my function and I'm multiplying it by 1/2, what I'm actually doing here is I'm taking every value that I had and I'm taking half of it. So now instead of it being what it was in the blue, it's only going to be half that value, which causes it to be shrunk. So again, emphasizing if it's bigger than 1, it's going to stretch. If it is a fraction between 0 and 1, it's going to shrink. So let's see what happens here. Once again, notice we have our x squared value. So hopefully by now you're like, oh, she's not going to say it again, but it's a parabola. The first one, I'm going to multiply every value by 3 after I plug it into the domain. And then the second one, I'm going to multiply it by 1/3. So the first one should stretch and the second one should shrink. So the purple here is my parent function. The purple one is my f of x equals x squared. Notice that my red value is when I'm multiplying it by 3. And my blue is when I'm multiplying it by 1/3. Now this might be a little bit hard to interpret because you might see that the purple one, which is my parent function, looks like I shrunk it, but I did not shrink it. I stretched it up. And one of the ways that you can remember this is I want you to think about what the slope would be. Let's say at this point right here, what would the slope be if I drew a tangent line? And see if I can draw a tangent line without it being too terrible. I'm trying. So there we go. There's the tangent line. That slope would have a value. Now notice if I came over here and I drew a tangent line and I tried to do the slope, this one is steeper than this one. Okay, this is steeper than this one. So my slope is higher at each one of those points when I'm multiplying it. So that's why it comes out like this. So take a look at this and think about the slope. Likewise, if I looked over here and I put a point and I were to draw a tangent line right here, and again, I apologize for my terrible art with using this, using the finger pad. Okay, so this slope here is going to be less steep than this slope. Okay, imagine you were hanging off of this or hanging off of this or hanging off of this. This is the steepest one. This is less steep. This is my parent function, and this is even less steep. Okay, so that's how you want to look at it. This, again, is where I'm shrinking it by taking it and I'm smashing it down really, and it becomes less steep. And this is where I'm stretching it and becoming more steep. Yes, and they tell you that that result would be wider than it would be when we shrink it, because I'm taking something and I'm just imagine putting your hand on top of some Play-Doh and smashing it down, it gets wider. But if I take that and I pull it up, then it's going to get more narrow. Okay, what about horizontal stretching and shrinking? We looked at the vertical stretching and shrinking. Now we're going to look at the horizontal stretching and shrinking. So you might have thought already that horizontal stretching and shrinking, I'm going to affect my domain before I put it into the function, and you're exactly right. So I'm going to take a value and I'm going to multiply it by the domain value before I put it into the function. So here I have the first one. Here is my regular function in blue. If I multiply it by a value that is bigger than 1, I'm going to actually take the ends and I'm going to shrink it in. Okay, so here, if it's bigger than 1, I'm going to take the value and shrink it in. Now, one of the ways I like to think about it is, again, slope. If I'm multiplying it by a number bigger than 1, the slope values on this graph right here are less steep than this graph. I'm making my slope more steep. And how do I do that? I shrink it in. The same over here when I look at my values where I have a fraction, so this is like 1/3, 1/2, 2/5, something like that. I'm taking it and I'm stretching it out. Excuse me. I'm stretching it out, and what I'm doing when I stretch it out is I'm making my slope at each point less steep. Okay, so now I have this crazy looking graph, and I want to see what happens when I multiply it by 2 and then when I multiply it by half. Now don't forget what I said. If I'm going to make the slope more steep, then I'm going to have to squish it together to make those peaks steeper. And if I multiply it by 1/2, I'm going to pull it apart to make the peaks less steep. Pretend you're climbing a mountain. So again, this mountain here is harder to climb because it's steeper. That's what happens when I multiply by 2. Here, when I stretch it out, this mountain's not as hard to climb because I made my slope less steep. Yet, what I have to realize is that I'm shrinking this over here, pushing it together like an accordion. So I'm shrinking it when I multiply by a number bigger than 1, or I'm stretching it out when I multiply by a fraction between 0 and 1. So now we look at even and odd functions. Whenever I put a negative value in for the domain and I still get the value, whether or not I would put in that positive value, if these two are the same, then I call it an even function. Why is that? Because it causes a symmetry here. If I put negative x and I still get the same value y over here as when I put in positive x, I get the same value y over here. They're at the same height, then I call that an even function. If I put in a negative value and I get the opposite, I call it an odd function. My parabola is an even function because I square x, but my cubic, x cubed, is an odd function because if I take a negative value and I multiply it 3 times, I still get a negative value. So here again is an even function. Notice the symmetry on this side. It's a mirror reflection on each side. This would be an even function. This is what an odd function would look like when you graph it. No surprise because our cubic graph looks similar to this. So determine whether they're even, odd, or neither. So right away I'm going to give you a hint. Look at the exponents. Both of these exponents are odd. Look at the second one. The exponent is even. And look at the third one. The exponent is even here, but it's odd here. So the first one, I get negative x to the 5th minus x. That would give me the negative of what I had when I factor that negative out. So that tells me it's an odd function. The second one, when I put in my negative value, I get the same thing that I had before. So it's an even function. So notice when I had both odd exponents, I got an odd function. When I had an even exponents, I got an even function. Now the second one had an even and an odd exponent. And it's not the opposite and it's not the same. So it's neither even nor odd. So you might have something that might not be even or odd function. It might be neither. So some of the graphs of functions in example 8 that they show, we have this graph here. We have this graph here. And we have this graph here. The graph of x is symmetric about the origin. And the graph of g is symmetric about the y-axis. But h is not symmetric about the y-axis or the origin. So it's neither even nor odd. So it's all about these axes right here. That's what I mean when I say axes. This one is symmetric about the origin. This one is symmetric about the y-axis, but this one is not symmetric about the y or the origin, so it's neither even nor odd. Okay, well that's it for this one, and now we're going to go on to the next week.